Hello everyone, myself Akash Reddy from Sri Venkateswara College of CSE AI Department. So today's topic is Hidden Markov Model, shortly known as HMM. So at first, what is HMM? So HMM is a static model that is used to describe the probabilistic relationship between the sequence of observation and the sequence of hidden state. It is often used in a situation where the underlying system or a process that generates the observation is unknown or hidden. Hence, it got the name as hidden Markov model. It is used to predict future observations or classify a sequence based on underlying hidden process that generates the data based on the given information. An HMM consists two types of variables: hidden Markov state and observation state. The hidden state are the underlying variables that generate the observation data, but they are not directly observable. The observation state are the variables that are measured and observed. So let's look into the applications of HMM. So at first we have handwritten recognition, speech recognition, gesture recognition, and motion video analysis and tracking, stock price prediction, optical signal detection, digital communications and music analysis, and DNA sequence analysis, and so on, etc. So let's go through a problem and let's implement it. So at first, the problem statement is so at first we are defining the model parameters. In this we have two states and two observations. At first state we are having sunny and the next one is rainy, and then when it comes to observation we are having the dry and the wet. In this example, the state space is defined as a state which is listed of two possibility weather conditions. One is sunny and the rainy, and the observation space is defined as observation which is list of two possible observation dry and wet. The number of hidden states and the number of observation are defined as constant. So as per we guys are getting the output number of hidden states is 2 and the number of observations are also 2. So next, the start probabilistic transition probabilities and the emission probabilities are defined as arrays. The start probabilities represent the probabilities of starting in each of the hidden state, and the transition probability are represented in the probabilities of a transition from one hidden state to another hidden state, and the emission probabilities represent the probabilities of observing each of the output given a hidden state. The initial state distribution is defined as a state probability, which is an array of probabilities that represent the probability of the first state being sunny or rainy. The state transition probability are defined as transition probability, which is 2 cross 2 array. Will be using 2D array representing the probability of transitioning from one state to another state. The observation likelihoods are defined as emission probability, which is 2D array again representing the probabilities of generating each observation from each state. So we'll be going through the implementing of the code. At first we are having the state. So at first we are having the state. Uh, we'll be defining the and initializing the state distribution. State probability is defined and we are initializing it by np array in format of array 0.6 and 0.4, and we are printing the state probability And same goes for defining the state transition probabilities and the observational likelihoods. The transition probability as np dot array in array form at 0.7 comma 0.3 comma 0.3 comma 0.7, and we are printing out the outputs. And next we are defining the observation likelihoods. Emission probability equals to np dot array format of 0.9 comma 0.1 of 0.2 comma 0.8, and we are printing out the emission probabilities. And as per we are guys are getting the output as state probability as 0.6, 0.4, and the transition probability as 0.7, 0.3, and 0.3 comma 0.7, which is a 2D array. And next we are defining the output for emission probability, which is also a 2D array, as 0.9, 0.1, and 0.2, and 0.8. So next we are going through define an observation sequence. Is a sequence of observation is defined as an 1D array numpy array. The observation data is defined as observation underscore sequence, which is a sequence of integers representing the corresponding observation in an observation list. Decode the observation sequence. The Vatibi algorithm is used to calculate the most likely sequence of the hidden state that generates the observation using the decode method of the model. The method returns the log probability of the most likely sequence of the hidden state and the sequence of hidden state itself. So at first we are initializing log probability hidden state, and then we are assigning by using the model dot decode of observation sequence, and length equals to length of observation sequence comma algorithm equals to whatever, and we are printing out the log probability and the most likely hidden status. As per we are guys are getting the output, log probability is minus 6.3606 and so on, and most likely hidden status is 01100. At the last we are plotting the result by using the PLT, which is matplotlib, which is basically used for creating a static animated and interactive visualization in Python, and SNS, which is a Seaborn module Python data visualization library based on the matplot. SNS dot set style is taken as a white grid, and plot hidden status minus o, and label has a hidden status, and plt.x label is as timestamp, and y label as most likely hidden state, and the title as sunny or rainy, and we are using to show the final output as plt.show. As per we guys are getting the output here. So at first in the graph we can see the x-axis as a timestamp and the y-axis as hidden likely most likely hidden state at first and so on.